In this section, we're going to summarize the wave-particle duality, both of light and for matter particles. So we're really just wrapping everything up, putting everything together in the end before we go on to our next chapter and take a look at the idea of a wave function. Now, looking at each of these, we have, of course, our light, which has a wavelength equal to Planck's constant divided by its momentum, or alternatively, the speed of light divided by the frequency. So light, of course, has a wavelength. We saw that in the Young's double slit experiment that was established. Matter also has a wavelength. De Broglie, his hypothesis, established that matter particles, particles with mass, have a wavelength also of Planck's constant divided by the momentum. And of course, because they have mass, we can write the momentum as mv. Likewise, each of these particles have an energy associated with them. For light, the energy is equal to h times the frequency. Because there is no mass here, that is really the energy associated with the particle. If a particle has mass, however, we have two forms of energy. We have the rest energy, the rest mass energy, the famous equals mc squared equation, which I think many people don't entirely interpret the right way. And of course, we have the kinetic energy. And if we add those two together, the total energy is gamma mc squared. Finally, light travels at, well, the speed of light, and matter cannot. Because it possesses mass, it must travel less than the speed of light. And, in terms of both of them, we really see the primary difference between the two is one particle has mass, one particle does not. One particle travels at the speed of light, one particle travels less than the speed of light. So that really shows that there's a tremendous overlap between both particles of light, photons, and particles with mass, matter. Now, it's interesting, I was thinking about this, and to my best knowledge, I'm only aware of light, which has been confirmed as a particle, obviously. It's traveling at the speed of light, but there's also the hypothetical particle called the graviton, also that is thought to travel at the speed of light. So that would be interesting to be able to compare and contrast to what we see here. Certainly with gravitational waves, if it is quantized, it could also be associated with a wavelength. But at this point, we have light, we have matter particles, matter waves, if you will, both possessing both a particle nature to them and a wave nature to them. So let's go to extending Young's double slit problem. And we're going to do the same problem again, but this time we're going to do it with electrons. Now, the electron double slit experiment was conducted by Klaus Jensen in 1961, where he was able to diffract electrons. But what's interesting is Richard Feynman, who's just a brilliant physicist who worked with quantum electrodynamics, talked about how a single electron would behave as it passes through a double slit. And he predicted it would still produce an interference pattern. So for instance, if we were to take an electron and pass it through the slit, it would have a higher probability where constructive interference would be predicted for a very large ensemble of electrons coming through the double slit, okay? And a lower probability where we see destructive interference. And essentially what it's saying here is that the electron possesses a wave nature to it. And as it passes through the double slit, this wave interferes with itself. okay? And it's not until the electron, and let's be very careful here, because in order to observe that electron, it has to interact with an atom or an electron within an atom. So it goes from something that is spread out to something that it can only interact with one other particle, okay? Atom, electron, whatever. If it's, maybe it's a phosphorus screen. And when that takes place, it goes from a larger wave to a more localized event. So that's sort of the interpretation that we have right here, that the electron, its wave function, as we'll talk about in the next chapter, extends over a very large part of space. But again, it's only going to interact on a very, very small scale when it finally gives up its energy. Again, it might be hitting a phosphorus screen. It might be hitting some type of detector, but there where it makes the interaction, that's going to be very localized. So the first double slit experiment with a single electron passing through double slits was performed by Giulio Pazzi in 1974. And the interesting thing to see, and unfortunately I'm sort of blocking this, is when these electrons go through the slit, at first, they don't appear to be producing an interference pattern. So, let's look at 6 electrons fired through the double slit, and we see 1, 2, 3, 4, 5, 6. Okay, just like single particles, which are randomly hitting the screen, and I don't really see anything necessarily special about them. We fire more through the double slit, maybe we can see a pattern. It's not really a very strong pattern. You could convince yourself one way or the other, depending on where you sat on, what your expectations would be. But clearly, it's difficult to pick out a pattern yet. Now, with more and more electrons, we begin to see a pattern, okay? What's happening here is very, very important, okay? The interference pattern represents really the probability of an electron striking that particular place. Where we have constructive interference, the probability increases. Where we have destructive interference, the probability decreases. And we still get electrons hitting in these regions of destructive interference, but we get fewer. And clearly, if we send enough electrons through, we can see here's constructive interference, here's constructive interference, here's constructive interference, here's constructive interference. Okay? And we are observing both a particle and a wave nature here. We see the particle nature where the electron hits the screen, interacts with one atom in the screen or one electron in the screen, and therefore gives off light as a result. We're also seeing the wave nature, the interference pattern, which is produced by the double slit. So beautiful experiment. You can do it. It really doesn't matter. You can do this with light. You can do this with individual photons with a sensitive enough detector. You can do this with electrons. You could even do this with other particles such as protons. But obviously protons have a very small wavelength for typical momenta, so it would be difficult getting an opening that small. But you will see this type of behavior. Now, one way to explain how can you have a particle and a wave at the same time? Well, we try to use models of the microscopic world, which are, familiar to us in the macroscopic world. So one of the first models of the atom was to represent it as a bunch of spheres, okay, hard spheres. Like, they had a very definite surface, and then below that, was pretty uniform. We use that model because that was something familiar to us. All right. But now we know that that isn't a great representation of what an atom really is. Likewise, when we think about waves, we oftentimes will use the analogy of waves on the surface of the water. But of course, when we're talking about light waves are more complicated than that. They have electric fields and magnetic fields, which are vectors. Certainly with a surface wave, you don't have, field vectors there. So again, we try to take something from our macroscopic world and apply to our microscopic world. So what we see with wave packet is something that's a better representation of what's going on. But again, only an electron can really represent an electron. It's like, when we think about looking at the Earth, we look at different parts of the Earth and we use maps to sort of guide us as to what's at a particular location. That map is a representation. It has its limitations in terms of what details it's going to include. So, take this sort of the same way as this is a map. It's a better map than a hard sphere or, the other way that we typically represent waves. But one model that I find appealing is this wave packet, this idea that the location of the wave, has some finite nature to it, but it also has an oscillation. And basically, if we were to take a pulse of some wave, sort of limit when it begins, when it ends, we would see, something very familiar that looked like this. Okay. So this wave packet, again, the idea that it's a package, it has maybe not a very definitive starting or end, but it has sort of a beginning and an end, which, is sort of in the line of what we imagine a particle to be, but also it has an oscillatory nature, sort of expresses the duality of both the photon and the particle like an electron. So again, as I said, this wave packet doesn't have an exact location, okay? And in fact, when we look at the Heisenberg uncertainty later on in the following chapter, we will see, in fact, that there's an uncertainty in the position, but there's also an uncertainty in the wavelengths of the wave packet, okay? So the location sort of spreads out, over a finite delta x, but we'll also see there's a finite bandwidth. Remember, momentum is related to the wavelength. So if we have a spread of wavelengths or frequencies, that corresponds to a spread of momenta. That's very much connected with the Heisenberg uncertainty, where you can't know the exact position with certainty, and also the exact momentum. One way to picture this is if we take our little wave packet again, just a model for what we think of these particles with a wave nature. And we look at the frequency. If we do a frequency spectrum of all the different oscillations that are in here, what we find is we don't have a single frequency. Really, if you study waves mathematically, a monochromatic wave would extend from negative infinity to infinity. It's a little bit hard to accept a wave that has existed from, negative infinity time to, going into the future infinity, or extend in space an infinite distance. But to be, single frequency, without any spread of bandwidth, that would be what we would require. And of course, nothing is like that. So if we have this little wave packet right here, this distance that it sort of, and this is probably, like a root mean squared average of the amplitude where that exists, is going to be inversely proportional to the spread of wavelengths that compose that little wave packet, and also the spread of frequencies that we have here. An interesting thing happens if you know anything about Fourier transforms. If you try to make this little wave packet or this little pulse smaller and smaller, it requires a larger and larger bandwidth. And that's something that we actually see with very short pulsed laser beams. The most narrow, temporally narrow, the shortest pulse of light requires a very large spread of frequencies to produce that narrow pulse. Again, a little bit beyond our discussion here, but going back to what we're trying to show here is that we can represent both a particle and a wave nature to both the photons and these matter particles. So let's take a look at a situation here. We're going to use this the application of wave and particle nature, mainly the wave nature of the electron, to improve on an earlier device that we talked about in the semester, and that was the microscope. So when we use the relativistic equation to calculate the wavelength of an electron traveling at about 2/3 the speed of light, we get a wavelength of about 2.72 picometers. Again, going back to relativity, if we plug in 2/3 the speed of light, we get a Lorentz factor of 1.34. We know that the wavelength is going to be equal to Planck's constant over the momentum. We've got to use relativistic momentum here because it's going very, very quickly. And we plug it into here. And for these types of electrons, we get 2.72 picometers. Okay, let's put that in perspective. The optical microscope, we take the wavelength to be about half a micron. Okay, that is 5 × 10⁻⁷ meters. Or if we want to put that in nanometers, 500 nanometers. If we want to put that into picometers, okay, we got to go another 10 to the 3 down. That is 500,000 picometers. With resolution, we're typically not able to see detail smaller than the wavelength of whatever we're using to look at an object. Could be light. In this case, it's going to be electrons that we're illuminating the target with. So theoretically, if we use electrons in some type of microscope, you know where I'm going here. Okay, if we use electrons instead of photons, we can achieve a much higher resolution. Now, unfortunately, with the electron microscope, the optics is achieved through electromagnetic interactions. Okay, so we actually use magnetic fields to steer and focus the beams, and this results in very severe spherical aberration. We talked about this when we talked about the invention of holography, that basically holography was invented as a way of correcting for some of the spherical aberration. But even with a very, very powerful electron microscope and with modern techniques of correcting with the spherical aberration, we're still sort of limited down to about 50 picometers in terms of the resolution. But that's incredible when we can consider that your limitation with an optical microscope is usually, getting around the micron range, okay? So going from 10 to the minus 6 in terms of resolution down to 5 times 10 to the minus 11, that's, 5 orders of magnitude improvement. You're able to see a whole new world from the micron range down to the picometer range. We can actually see individual molecules and atoms under the right conditions. So here's the electron microscope. And think about your regular optical microscope turned upside down. Here we have what would be, analogous to a light source, okay? We're not using photons, we're using electrons. So we need an electron source, and that, of course, is an electron gun. Sounds more high tech than it really is. Electron guns were found in old CRT televisions, and they really just consisted of a negatively charged cathode, a positively charged anode. The electrons would be attracted from the cathode. Cathode would be heated. They would be accelerated toward the anode. We got a little mini particle accelerator here, if you will. So here we're shooting off the electrons at a fairly high velocity. The next thing that we would do is, because these electrons want to diverge, we would try to focus them with a lens. Now, remember, the way we achieved focusing in optical microscopes was to use convex lenses. We could also achieve focusing with telescopes using concave mirrors. We don't have dispersive type media for the electrons, or at least we don't have dispersive type media that I'm aware of that isn't going to absorb all the electrons. Electrons are going to want to interact with matter pretty vigorously. So we've got to use other techniques. We'll see how these electromagnetic lenses actually work. After the light is collimated, we then focus the light onto the specimen. And then finally, we use an objective lens and then project the image onto a fluorescent screen or some other type of detector. So where the optical microscope, you would be looking through the eyepiece, okay? And, your objective lens and the projector lens is really replacing the eyepiece here. This sort of is turned upside down. So how do these magnets work? Well, we know from the Lorentz force, the force on a charged particle is going to be V cross B times Q. The electrons have a elementary charge. So as the electrons come through a magnetic field, they're going to feel a force which is perpendicular to their direction of travel and the magnetic field. This is a dipole magnet, and all the dipole magnet is going to do is deflect the beam. Now, I had the great fortune of working at a particle accelerator out in Los Alamos. And one of the neat things I was able to do was actually to focus the beam at one of the target areas. And I was just a student, and one of the operators who was working on this took a group of us as students and allowed us to adjust the magnets which were used to focus. And for these types of beams, we would actually use what are called quadrupole magnets. So you'd have a south, a north, a south, a north, and that would surround the beam. And then these would come in pairs of 3. And this would allow you to converge the beam or diverge the beam. And essentially, the dipole magnet would have a large amount of spherical aberration, but you could use, a few, they come in triples, is what they would come in. And we would just keep adjusting them using photographic paper on the target till we had a very nice, clean beam for what we wanted to hit. So, long story short, in particle accelerators, we usually use quadrupole magnets because we have long distances that we can use to focus the beams. However, in this electron microscope, these things sit on top of tables. So, given the very short distances, a quadrupole magnet, I'm speculating here, folks. So if there's an expert on beam optics, if you want to chime in the comments, that's fine. But I would suspect that a quadrupole magnet would just be very, very difficult to use on such a short distance for a tabletop electron microscope. So what we do is create these magnets, and I'll show you how these work. First of all, we have coils of wire which wrap around the cylinder, and then basically the magnetic field comes out of these two poles right here, and going from north to south, they're pointing in the direction that the beam is traveling. So as the beam comes through, it is going to experience, and this is wrapping around. I couldn't draw this in 3 dimensions. I could only do sort of a 2-dimensional cutaway of this, but you can see how the magnetic field pushes into the beam, and that has the same effect as a converging lens would have, where, as a beam is diverging, you can see an electron beam coming in diverging. This magnetic field, which is pushed inward by this very specialized magnet, sort of creates a pinching on the electron beam and effectively allows you to focus it, okay? And again, it's symmetrical all the way around. And these lenses do have a large amount of spherical aberration. Again, I'm not an expert on beam optics, but these behave like spherical convex lenses. So here is a highly schematic diagram of what takes place here. These lenses, I'm showing them all to be, they're magnets, what they really are. There's no glass in them. When I say lens, I'm saying that they really have effectively the same behavior on the beam as a convex lens would have on a beam of light. But I'm showing them all to be the same, and really they're not. Depending on where they are in the staging, they will have different shapes. They have different focal lengths, is what I'm really trying to say here. But you also might have multiple lenses. Again, highly schematic. So we have our electron gun. We have our condenser lens, which is going to focus the beam onto the specimen, onto the location of the specimen that we want. And I think this is typically a grid-like material. The beam hits the specimen, so it's really analogous to illuminating our target, or our object here. And the electrons, which are scattered off the target, are then sent through the subjective lens. The objective lens forms a real image with the intermediate lens, and then that is projected again as a real image onto some fluorescent screen. Originally, they were fluorescent screens because that was a very easy way of converting the energy from the electrons into light, and you could then take a photograph of that. I suppose you could replace this with a detector array of some sort, or some other means of visualizing the electrons. But again, a fluorescent screen is such an easy way of converting the electron intensity into a visible intensity that can either be viewed visually, photographed, or recorded digitally. And this is amazing. This is the lipid bilayer. Okay, so every cell has this phospholipid membrane that surrounds it. On the outside, you have you've got to remember my biology, it's been a while, but you have the polar end on the outside, you have the lipid end on the insides of the membrane, and basically this is what surrounds your cell. This is what surrounds the nucleus. This is a structure where you're actually seeing it on a molecular level. Not quite sure what this is. A plasma membrane. Don't know. But in any case, this is a resolution that at less than 5 nanometers that you could never hope to achieve with a optical microscope. Oh, just a side note, one interesting device, I guess you'd call it, or it wouldn't be it's really an optical microscope in the X-ray part of the spectrum, is we are starting to achieve very, very high resolutions with electromagnetic waves in the form of X-rays, using very expensive accelerators, using what are called synchrotrons. These generate very bright X-rays, and then they've actually created X-ray microscopes using mirrors. But again, the electron microscope has been really the gold standard of instruments to view objects in a very, very small scale. And by the way, this is the transmission electron microscope. The scanning electron microscope works a little bit differently. With the scanning electron microscope, which doesn't have the same resolution, but is better at revealing surface detail, the electron beam will actually be scanned, what we call, a raster. It'll be scanned across the surface of some specimen, and that specimen is usually covered with, conductive particles like gold particles, and it'll give you very high detail of the surface features, whereas a transmission microscope, pretty much does what you're seeing right here. The electrons are being passed through the sample rather than being scattered off the surface. There's also the scanning tunneling microscope, which uses a probe to vary the current between it and whatever sample it's using. But to the best of my knowledge, the transmission electron microscope has the highest resolution of the transmission versus the scanning electron microscope. And one difficulty with our transmission microscope is we have to prepare the samples to be placed in a vacuum. And, if you put living tissue in a vacuum, and many times what we're using these electron microscopes is to look at biological tissue. Biological tissue is not very compatible with a vacuum. What happens when you place biological tissue, which has many volatile materials, water is a volatile, other volatiles in there, they're just going to evaporate off, and your sample's probably going to be destroyed very, very quickly. So we either have to dehydrate these samples to be placed in a vacuum, so they're not going to give off any volatiles. But another technique is to operate these at very, very low temperatures where the vapor pressure of any of the volatiles is extremely low and it can actually survive a vacuum. So it's not like you can take pond water, put it on a slide, put it under the microscope like you can with an optical microscope and take a look and see what's happening here. These samples are basically in a vacuum because the electrons can't propagate through air very easily. They're gonna run into a lot of problems when you try to do this. Okay, so that's my best explanation of electron microscopy. I'm no biologist, so take what I say with a proper grain of salt. But it's really an excellent example, an excellent application of how the electron has both a particle nature and a wave nature to it.